How wonderful it is that nobody need wait a single moment before starting to improve the world. Anne Frank. And replacing carbon source energy with cleaner energy is as good as any challenge in the world at this time to start. According to the United States Energy Information Administration, in 2017, about 84% of the electricity generated by utility-sized power plants in the United States was done through the burning of fossil fuels or the use of nuclear energy. Unfortunately, the first method produces high amounts of carbon dioxide, a known cause of global warming, as well as other pollutants. While nuclear power plants contribute nearly nothing to global warming, they do, however, create many tons of radioactive waste that must be kept contained in specialized storage areas. In a world where it seems like the need for electricity is continually growing, we are still using methods of producing it that seem to be leading to the world's very destruction. Even though some states, like California, have upped their reliance on renewable energy sources, nationwide only about 16% of our electricity is generated by alternative methods such as hydroelectric, wind, and solar that do not contribute to global warming. Wouldn't it be great if we could come up with a new, non-polluting way to create substantially more electricity to add to this total? Nicer still, what if this new way to create electricity would cost about the same to produce as other green forms of electricity generation, or even less, without the need for any additional infrastructures that typically create their own issues of habitat destruction, or the expense of building more dams? And how about if it could also create energy even when the sun wasn't shining, the wind wasn't blowing, and the lake was dry? You might be surprised to find out that there is such a method, using compressed air. Yes, compressed air. An ordinary diesel electrical generator set like this one can be easily converted to run on compressed air only, and the residue left over from this air expansion process is plain air. The same air that goes into powering the generators comes out the other end. No extra hydrocarbons, no acid rain, no radioactivity. Compressed air can be stored for long lengths of time without degenerating. So if you make more than you need for on-demand use, you can store it up for later until you do need it. And unlike oil and natural gas, compressed air will not catch fire or explode if it should escape from its storage tanks and pipelines. So if you can figure out a way to compress air efficiently, day in and day out, no matter what the weather, you have then most likely discovered a way to generate electricity that is much cleaner, safer, and reliable than most of our other options. The U.S. Department of Technology praises compressed air as being clean, readily available, and simple to use, while at the same time it acknowledges it as being the most expensive form of energy on the planet. Until now. Our team leader has come up with a way to create compressed air using railroads that multitask, so that they can also power cities and towns at about the same cost as existing methods of generating electricity with none of the drawbacks. Moreover, much of the infrastructure is already in place all over the country and much of the civilized world. And railroads are remarkably reliable. When trains are delayed, it means money is lost. So railroad companies are very diligent in making sure that railroad traffic, especially freight traffic, gets where it needs to go, when it needs to be there, regardless of the weather or time of day. Our new technology uses a series of 12-foot-long, patented air compression sections attached to the inside of each rail. These air compression sections are basically a durable type of spring-loaded hose, topped with a long-lasting tire tread-like surface for flexibility and quietness, along with a support structure that allows for the air compression section to be attached safely and easily to the railroad tracks. As the train passes over each air compression section, the larger diameter inside portion of each train wheel presses down, acting like a rolling pin, squeezing the air in the hose along ahead of it until it comes to the end of the section and the air is shunted past a one-way valve. As soon as one set of train wheels has gone by, the spring-loaded hose recovers its shape and refills with air before the next set rolls over it. After passing the one-way valve, the compressed air is fed into underground storage vaults that can be located alongside the railroad tracks or wherever is convenient. Eventually, the compressed air will be routed to a bank of pneumatic motor generator sets where it will be used to generate electricity. Let's see how this system might be used to furnish the electricity needs for a typical American city of 100,000 residents. An average town of 100,000 residents would be comprised of around 40,000 households. In 2017, the average electricity consumption for a U.S. residential utility customer was around 10,000 kilowatt hours per household per year, or about 30 kilowatt hours per household per day. To supply 40,000 households in our model city with 30 kilowatt hours of electricity per day, we would need to produce an average of 1.2 million kilowatt hours per day. Since households go through peaks and valleys of energy use based on the time of day and the season of the year, the actual size of a power plant needed would have to be based on peak usage to make sure that on a day when every house had their air conditioner or heater running, there was still plenty of electricity available. Since a single diesel generator set that has been modified to run on compressed air can produce about 85,000 kilowatts per hour, we would need at least 18 modified generator sets in place to be able to meet the peak demand of our hypothetical city of 100,000 residents. These generators could be broken up into several smaller capacity power plants and placed at different locations near the railroad line, or all of them could be housed in one building about the size of a football field. On most mornings, only a few of the generator sets would need to be in operation, but as the city wakes up and the need for power increases, the generator sets can simply take in more compressed air to meet the rising demand, similar to the way an automobile's cruise control adjusts the fuel supply to the engine, responding to the ups and downs of the highway. As the day progresses and more capacity is needed, additional generator sets can be brought online at the touch of a button, since the compressed air to run them will be instantly available from storage. To supply that many generators with compressed air at a targeted mid-range of 330 pounds per square inch, we estimate that we would need to outfit around 27 miles of railroad track with our air compression technology. And there would have to be at least 24 trains of 50 cars each passing over the tracks in every 24-hour period, or some combination equaling the same number of wheel sets. You might be wondering how enough compressed air to supply the electricity needs of a city of 100,000 can be created without greatly adding to the amount of diesel fuel that the trains are forced to burn while they are passing over our air compression sections. One reason why our method of creating compressed air can be done so effectively is because in the best locations, the energy that we will be drawing upon comes either from the process of slowing the train down to a safer speed, such as in coming down from a mountainous region or approaching curves, or when coming to a stop at a train station. But mostly, since the majority of our air compression sections will be located in areas where the trains will be going along at highway vehicle type speeds, we are relying on the fact that the immense momentum created by the train's motion plus its cargo will far overwhelm and offset the minimal resistance created by our equipment. Our calculations show that the extra burden of passing over our air compression sections would only cause the burning of between 2% and 10% more fuel during the time the train was doing the extra work. Trains are remarkably efficient at moving freight around the country. They typically report to the government annually that they average 470 miles per gallon for every ton of freight they carry. And that includes all the starting and stopping that must be done on a typical trip. When they are cruising along in the flat ground portions between stops, they are getting even higher miles per gallon rates. As each train approaches the tracks outfitted with our compressed air generation system, we will expect that it is getting at least the industry average of 470 miles per gallon of diesel fuel for every ton of freight it is carrying. A train of 50 fully loaded freight cars weighing almost 7,000 tons would normally burn 385 gallons of diesel as it passed over 27 miles of track. In a worst-case scenario, let's assume that as the train passes over our air compression system, it has to work 10% harder and cuts the ton miles per gallon down to 420. That means each train will burn an additional 45 gallons of fuel as it passes over our tracks. Over a 24-hour period, at 1 train per hour, our system would compress enough air to create over 1.2 million kilowatt hours of electricity while making the trains only burn an additional 1,080 gallons of fuel. The system is even more efficient when the cars are not fully loaded. A 50-car train of empty freight cars would only burn an additional 12 gallons of fuel for a total of 288 extra gallons of fuel per day. At the present time, the cost of diesel fuel nationwide is around $3 per gallon. Even though train companies can probably buy their fuel at a volume discount, let's assume they have to pay the national average. The cost for the fuel to generate 1.2 million kilowatt hours of electricity for a model city using railroad cogeneration would come out to a number between $864 and $3,240 per day, depending upon how fully loaded the trains were during that 24-hour period. By comparison, it takes about 1 pound of coal to generate a single kilowatt hour of electricity. A coal-burning power plant would have to burn over 1 million pounds of coal to produce 1.2 million kilowatt hours of electricity. That's over 500 tons of coal, enough to fill at least 5 railroad cars. At a cost of 2.2 cents per pound of coal, it will cost the coal-fired power plant over $26,000 just to buy the coal it needs to keep our city supplied with electricity they typically demand for a single day. It takes 1.6 cents worth of natural gas to create 1 kilowatt hour of electricity. Therefore, it will cost the natural gas power plant around $20,000 a day to purchase the gas it needs to supply our town with electricity. Now let's look at the savings in terms of carbon dioxide put into the atmosphere. Burning coal at the coal plant would add 2 million pounds of carbon dioxide to our air per day. Burning natural gas at the natural gas plant would add 1,425,000 pounds of carbon dioxide to the air. Burning the diesel fuel to make the same amount of electricity via railroad cogeneration would only add 22,000 pounds. That's 99% less than coal, and 98.5% less than natural gas. In terms of safety and liability, the transportation and storage of compressed air poses virtually no risk. And as for power plant fires and explosions, it also poses virtually no risk compared to either natural gas or coal. And since railroad cogeneration facilities can be safely located in the vicinity of cities, there won't be the need for hundreds of miles of ugly and costly high-tension lines or their associated risk of starting dangerous wildfires. In terms of infrastructure, one of the biggest costs has already been solved, simply by the current presence of railroad lines in connecting just about every urban area to each other in the United States and the world. The other big infrastructure cost associated with the railroad cogeneration system would have to do with the storage of the compressed air. To meet the possible peak demands of a city of 100,000 people, plus have enough excess capacity to keep electricity flowing for 3 extra days if the railroad train stopped running, we would need to build 2 storage vaults 50 yards wide by 25 feet deep by 6 miles long. This, of course, would be a huge undertaking. These storage vaults could be made smaller if one or a combination of any of the following options were put into place. The air was compressed to an even higher PSI. If a way to store the air deep underground in unused wells or caverns could be made available. If a certain portion of the compressed air were used to generate excess electricity that was then captured by some sort of alternative storage medium, such as lithium batteries. If the need for excess compressed air storage was lessened from 3 days to a lower number. Or finally, if the railroad electrical cogeneration system was not expected to supply the entire needs of the city during peak use hours, but was rather used as a main supply for non-peak hours. One nice thing about this new method for creating electricity is that the additional infrastructure will not create a massive eyesore on the visual environment. We wouldn't have to build large arrays to catch the light or wind, or new dams that fill up our scenic canyons. The equipment that will be seen above ground will pretty much look like the railroad tracks you see already. And the storage areas for the compressed air can be buried underground so that the land above can still be used for farming or other uses. It is our estimate that the railroad cogenerated power could be produced for around 4 cents per kilowatt hour, which is in line with the costs incurred by other producers of electricity. At the present time, electricity is sold for between 6 cents and 12 cents per kilowatt hour, depending upon the season, time of day, and the buyer. Even taking the lowest sales price of 6 cents per kilowatt hour, our plant serving our hypothetical city would make a profit of $24,000 per day, or almost $9 million per year. In addition, since we would be removing almost all the carbon dioxide that would have normally gone into the air created by fossil fuel burning power plants, There is good reason to believe that we would also benefit from any carbon credits that will be likely made available in the future. Since microgrid power plants running on compressed air can boast a minimal carbon impact while producing power at highly competitive prices, it is extremely likely that community choice consumers will prefer buying our cleaner form of generating electricity over the alternative forms like coal and natural gas. In the United States alone, there are over 233,000 miles of railroad track. If just 1/3 of that track were placed into railroad cogeneration service, we could then create 3,000 similar power plants and serve 300 million people, almost the entire United States. By doing so, we could reduce the number of power stations currently running on coal or natural gas by 90% and take a significant bite out of the amount of carbon dioxide we have been putting into our atmosphere. So, in conclusion, railroad-powered cogeneration of electricity shows promise to be not only a profitable business, but also one that contributes mightily to the improvement of our world as well. Thank you for your time and consideration. If you are interested in finding out more about this revolutionary method of creating electricity, please contact us at the address shown.